So taking a look at a retrosynthesis problem, if we're working one step back, first thing you want to look at is notice the relationship between the two substituents. If you notice between them, they're paired to each other. So that means an electron donating group somehow got that to go. And so you look at the two groups. This is an alkyl. That's a carbon of a carbonyl. So this is the electron withdrawing. This is electron donating. So this would have to come on at the end, last probably. Then also it's kind of weird too here because this is all of a sudden an OH on the less substituted carbon. So that should also pique your interest too. That reminds you of a reaction that you maybe know. Having that OH on less substituted carbon. That's an anti-Markovnikov product. So that would come from if we had the carbonyl still on there, that would come from this, from an alkene. Then one step back from this would be taking the carbonyl off, carbonyl group off. One step back from this would be probably you don't know ways to add, right? For Friedel-Crafts alkylation, right, and carbocations, right? This carbon right here that's sp2 hybridized, so that had to come from an elimination though. So one more step back would be, sorry, a little ugly benzene ring there. The bromine there. I'm gonna run out of room here. Sorry. So I'm not done yet. I'm still at this, which could have came from that, which could have came from the benzene ring. Going forward with this is a Friedel-Crafts alkylation, right? Because Friedel-Crafts alkylations only involve sp3 hybridized carbons. So it would be a chlorine, and I need 2 carbon pieces, an AlCl3, that's a catalyst. Here I need bromination, so that's that MBS in the benzylic position. If I zoom back in over here, right, back there, do this, I need a large bulky base, maybe something like LDA, lithium, diisopropylamine. Any sort of bulky reactive base would do that. Friedel-Crafts acylation, I need the chlorine, and I need that ketone, and AlCl3 again, which is a catalyst. And then here to have it add anti-Markovnikov, I need that BH3 and NaOH, and that gives me that anti-Markovnikov alcohol addition. Showing 4 dienes here, and the question is, which is most reactive, and rank them. So which is most reactive, and try to rank those. So it's actually very similar to looking at a benzene ring and just think about electron donating groups, electron withdrawing groups. So if I label these A, B, C, D, A is neutral, right? There's nothing really on it, the diene. B has a methoxy on it. C has a methyl, and D has 2 methyls. So methyl versus methoxy, which one's more electron donating? The methoxy is, that's right, the lone pairs. So B is going to be the most reactive, so increasing so if I rank them in order of increasing reactivity, so the question asks, this is on top hat, B would be the most reactive. Which one would be the least reactive? A, because there's nothing adding to it. And then it's C or D, which one's more reactive, C or D? D, 2 methyls is more than 1, so C is in the middle. Right, so it's just a matter of electron donating groups and evaluating them based on how well they do that. Diels-Alder question, so you can clearly see a diene and a dienophile. So the first thing I always do with the Diels-Alder is number the carbons, especially the diene and the dienophile. Diene, of course, has 4 carbons. Dienophile. I try to see if there's any differences in them, right? So if I do any resonance structures to try to identify the most electron-rich or electron-deficient carbons. So the diene, is there any difference between these? It's symmetrical. What about the dienophile? Is it symmetrical too? So there's no difference between 5 and 6. Okay, so now I just need to draw arrows to show, right, this cycloaddition. There you go. Easiest thing to do first is always draw the product of a Diels-Alder reaction, the 6-membered ring. And it forms a pi bond. So I'm going to turn this around. It'd probably been easier to actually redraw this if I wanted to. I would have done that, just redrawn it and turned it around. So I flipped this around. So this would be 1, 2, 3, 4. 1 is now bonded to 5 and 6. 6 is still bonded to the carbonyl, and so is 5. And the other side, there's this. Now, the thing to remember here, not to forget, is what else is bonded to 1 and 4. So we can call these 7 and 8. This is one of those things where in a Diels-Alder reaction, right, we make a ring. But if you already started out with your diene in a ring, then that ring doesn't get lost. You create a bicycle. So we got to find carbon 7 and 8 are actually still attached to 1 and 4. So there would be 7 and 8. Now another way, I can draw this in a 3-dimensional picture. All right, so one way to think about it, you could think about these things as coming out at you. 2 bonds kind of coming out at you, like a bridge. So I can draw that in a little fancier way. One, 2, 3, 4, 5, and 6. Now another thing that's important, actually, there's another stereochemistry piece here, that if you let this reaction just take place, if you don't see what's going on, remember we talked about the endo-exo approach? Most things, the kinetic product, at the lowest energy transition state, when it's cold, you're going to get the actual endo product. So these hydrogens are pointed up, you actually get the endo product. So this came underneath the forming pi bond. Right, when this came in, it came in the opposite way. It actually didn't come in with this pointed away, it came in with this pointed towards it. That's how this ends up underneath. This is the kinetic product because it comes from the lowest energy transition state. The other product, or the exo product, even though, right, this, you can tell this is kind of unstable, this being underneath here. Right, that axial, kind of pseudo-axial position. So this is a less stable product, but it comes from a more stable transition state. Thinking about aromaticity. So a series of molecules here, what are they? Aromatic, anti-aromatic, or non-aromatic? So what is what? Aromatic, non-aromatic, anti-aromatic. So let's look at A. What is A? Aromatic, non-aromatic, or anti-aromatic? Anti-aromatic, right? Because where's boron at in the periodic table? Boron has an empty p orbital. So that's like a carbocation, and that's an even pair. So this is actually, and right, it's too small to get out of the way. So this is actually anti. What about B? What is B going to be? B is actually aromatic then, right? B is aromatic because, right? How many electrons are in the system? 2, 4, 6, right? 6 will work. 4m plus 2. Oh, there's an odd number of pairs of electrons in the system, so that's aromatic, right? Because again, this is like a carbocation. Boron's like a carbocation. Essentially, it has an empty p orbital. sp2 hybridized empty p orbital. What about this one? Aromatic, anti-aromatic, or non-aromatic?
Non-aromatic.
Non, because it's big enough where it can get out of its own way. Right, non-aromatic, so it's gonna pucker, so it's not planar. Right, one of the things that are required for aromaticity has to be flat, planar, in a ring, and everything has to be conjugated. Right, which brings us to the next one. Right, so C is non-aromatic. What about D? What is D? Aromatic, anti-aromatic, or non-aromatic? Non-aromatic. That's right. Right there, that's sp3 hybridized, so that's not a conjugated system. Yep, it wouldn't be acidic, because if it had a negative charge there, then it would be an anti-aromatic system. It could be, so, or it would be non-aromatic probably. But the next one, what's this one going to be? Aromatic, anti-aromatic, or non-aromatic? I'm going to say non. I would probably accept anti, but this is still kind of this is a 7-membered ring. What is it? 1, 2, 3, 4, 5, 6, 7. I think it's close to that borderline where it could maybe pucker itself to get so it's not planar. So I would say non, but anti's probably okay too. So it'd probably be big enough to like make itself so it's not planar. All right, let's take a look at a benzene ring. So we're going to do an electrophilic aromatic substitution, an EAS reaction. So we're going to add something to the benzene ring and substitute off a hydrogen. And we need the super electrophile to do that. And in this case, it's going to be an oldie but a goodie. An alkene reacting with H+. And H+ here is actually a catalyst. I should write that in there. So the first step is going to be the alkene, the pi bond, reacting with the H+. That's going to, of course, form a carbocation. And which carbon are we going to go make the carbocation on? The more substituted one. All right. Do I need to do a rearrangement, or so what kind of carbocation do I have? Tertiary. Should I do a rearrangement? Right. So one thing I don't need, if I do a rearrangement here, it's just gonna make another tertiary carbocation, so it's not gonna make any difference. So we don't move sideways; we only go downhill. So we're gonna stay with this. This is gonna be reactive enough, right, to react with our benzene. Then our first step. You don't need to worry about ortho, meta, or para because there's no groups on there. We can draw some sigma complexes out. I would add, right, I made this maybe look this a little more simple than it was. Numbering your carbons is really important here to make sure you don't lose something. Right, so make sure you number the carbons here so you don't lose a carbon. It's a surefire way to not earn the points you need. One sigma complex. Keep moving the pi bond around, doing these intermediate resonance structures, which are specially called sigma complexes. And we know at the end of the day we're not done with the mechanism, right? So these are 3 sigma complexes. And we know we're not done because H+ is a catalyst, and plus we know we need to lose the H on here to fulfill the substitution reaction. So the last thing that's going to happen is this H is simply going to fall off. So those 3 sigma complexes are bracketed up because they're intermediates. So the final product will be those. All right, and you've regenerated the H+, right? And you've done an electrophilic aromatic substitution and added a carbon piece. Aromaticity again, taking a look at 3 compounds. So A, B, and C. Aromatic, anti-aromatic, non-aromatic. A is? It's non-aromatic. It's non-aromatic because what's the hybridization state of that nitrogen? Has to be sp3. There's no p orbital. So it's an uninterrupted system now. So it's an interrupted system. So this is a non-aromatic because that nitrogen has to be sp3. There's no p orbital, so it's not fully conjugated. What about B? B is aromatic, anti-aromatic, or non-aromatic. B is aromatic. That's right. And C is non-aromatic. And don't get lost. There's the sp3 hybridized carbon sitting there. Don't get lost along the weeds. So this is non-aromatic too. Good.